The simulation approach can be used to study the 16th century when such a problem arises. Another interesting example of Monte Carlo technique. Now throw some coins. Examples are only to show the simulation approach can be used to study almost any problem that involves uncertainty. It is a powerful technique to analyze large and complex real-life problems which cannot be solved by usual quantitative methods. Simulation can also be used when the real system is inaccessible or too dangerous to assess, or when a system is still in the design or theory stages. As I think it is one of the great illustrations of human brain. It is the only remaining tool when all other techniques become intractable or when they fail. Simulation is the process of designing a model of a real system and conducting experiments with this model for the purpose of understanding the behavior for the operation of the system. The use of the word simulation can be traced to the mathematicians von Neumann and Stanislaw Ulam in the late 1940s when they developed the term Monte Carlo technique while trying first to break the casino at Monte Carlo. Monte Carlo is a resort situated on an escarpment at the base of the Maritime Alps along the French Riviera on the Mediterranean, just northeast of the city Nice in France. The Monte Carlo technique has proved to be a very powerful technique in statistics to solve complex numerical problems with the help of random numbers. It is used in those situations where it is not possible to gain practical experience because one is dealing with problems which have not yet been arisen, to study transitional process, to assess the performance of certain procedures, and bootstrap the jackknife techniques for estimating variances of estimators in complicated cases. Monte Carlo technique is very powerful and is based on simple principles. Let us take a simple, interesting example of it. Let us take ourselves in past. In the 16th century, when James Bernoulli was not yet born, and so binomial distribution was not yet known to us. Suppose a problem arises that if 5 unbiased coins are thrown, what would be the probability of having heads on exactly 3 coins? Had binomial distribution known to us, we could have very easily obtained this probability. But as we are living in the age of pre-Bernoulli era, binomial distribution is not yet known to us. Then how can we find this probability? There is one way out. We can take 5 unbiased coins, throw them all together sufficiently a large number of times, and each time observe whether head on exactly 3 coins were obtained. The proportion of the number of times that head is obtained exactly on 3 coins would be an estimate of this required probability. But suppose there is a problem. The problem is that we do not have 5 unbiased coins with us. Nor we can get them by any means. Even if they are available, for some reasons, we are not allowed to use them. Now the problem seems very difficult. How can we find this probability of getting head on exactly 3 coins if 5 unbiased coins are thrown? Really a difficult problem. Neither the formula for obtaining this probability is known, nor we are permitted to throw coins. Then how can we find this probability? Here, in this difficult situation, the Monte Carlo simulation technique can be used to find an estimate of this probability. It is like this. There are 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Out of which 5 digits 0, 2, 4, 6, and 8 are even. And the remaining 5 digits and 9 are odd. If a digit is chosen randomly, the probability of being it even is obviously 1 by 2, and that of being it odd is also 1 by 2. Let us assume that getting an even digit would mean getting head on a coin, and getting an odd digit would mean getting tail on a coin. The probability of getting an even digit and that of an odd digit conforms respectively with the probability of getting head and that of getting tail on a coin. In this way, since the number of coins is 5, 5-digit numbers may be selected randomly sufficiently a large number of times, and in each number the number of even digits would be counted. The proportion of the numbers having exactly 3 even digits would be an estimate of the probability of getting heads on exactly 3 coins. In this way, simulation can be used to experiment on a model without going into the physical illustration of it and without incurring the cost of operating on the system. Another interesting example of Monte Carlo technique is determining the area of an irregular shaped land. There is no any definite formula for measuring the area of irregular shaped land. Now here what we will do, we would enclose the given area by some regular shape whose area is known, such as a square, rectangle, circle, etc. Now throw some coins or pebbles, say capital N in number, at random in the determined regular shape, and count the number of pebbles falling in the irregular shaped land. Suppose it is a small n out of capital N. If capital N is sufficiently large, and if the pebbles are thrown strictly at random, then the ratio of the number of pebbles falling within the irregular land, I mean irregular shaped land, to the total number of pebbles thrown, that is a small n by capital N, would be the same as the ratio of the area of the irregular shaped land to the total regular shaped land. And so, an estimate of the area of the irregular shaped land can be obtained as a small n by capital N. These two examples are only to show that how beautifully the simulation method works to solve the problems. There is a wide range of applications of computer-based simulation models because it is an approach rather than an application of specific techniques. This technique is used for forecasting, which takes into account risk, uncertainty, and variability. Project managers and decision makers use the Monte Carlo simulation tool to estimate the impacts of various risks on the project cost and project timeline. Thank you.